On Tuesday, when I explained this stuff, I'm motivated by the geometric aspects of directional derivatives and graphs and tangent planes and tangent lines. So now I want to start with sort of a slightly different end, which is one of the applications of this technique. In other words, what is a real life situation where we might be interested in finding directional derivatives? And I explained last time that directional derivative is just a fancy term for the rate of change. And so here is a typical example, which you may have already seen in the book or in your section work, which is imagine a mountain. Imagine a mountain. Okay? And then there is the ocean somewhere next to it, and the beach. But we'll talk about this later. Focus on the mountain for now. Okay, this is a mountain. Now, if I draw it like this, it's not clear whether it is a mountain or just a curve, right? So in order to give it an illusion of 3D, of three-dimensional picture, what I usually do as a reflex, and what you would normally do, or when you read the book, what you see there, is that you draw some curves on it. You're kind of trying to give it a three-dimensional feel, right? So my first point is, what are these curves? These are the level curves. So that's the first thing I want to say, which of course is sort of, I've said it before, but I just want to emphasize it one more time. Even to visualize this three-dimensional object on the plane, we find it very convenient, very useful to imagine not just the contour, the general contour of this object, but this collection of curves which are kind of parallel to each other. And what are they? Were they just obtained by taking the section of the mountain by parallel planes, by parallel horizontal planes, which are parallel to the floor, to the ground. Okay? That's what they are. Well, in fact, I have drawn just the visible part, the visible parts of those curves, right? There is also a backside for each curve. For example, this one also has a backside, but we don't see it unless it's a transparent object. We don't see it. So that's why usually we indicate like this, right? So each of them is actually has a, sort of the second half, which is behind, which we don't see. And this we also don't see when we look at the actual mountain. But when we try to draw the picture, then we draw this. Okay, so that's the first point. So the second point is what does it have to do with directional derivatives? Directional derivative is the rate of change. So change of what? So in this particular setting, there is a very good example of this, which is that suppose that there is somebody here on this mountain who is climbing it. Okay, so there's a climber. And so the climber wants to decide which way they should go to, and depending on which way they go, what will be the rate of the, how steep will be the climb? Will the climb be? That's the question. So the rate of change will be here the rate of its altitude change, or his or her altitude change, right? And the higher the rate, the steeper is the climb, in case we are going towards the top of the mountain, or the steeper the descent, if we're going down. And likewise, the smaller the rate of change, the smaller is the steepness. So how do we measure this? The point is that there isn't a single number. There isn't a single number to give us the steepness of the climb, because the climber could go in many different directions. And for each direction, there is a particular steepness rate. For instance, the climber may be tired and doesn't want to climb anymore. So in that case, the climber could just go along the level curve. So then the altitude of the climber, the height of this point over the sea level, will not change at all. So then the rate of change, or the steepness level, is 0. Steepness rate is 0, right? So that's one possibility. That would correspond to going in this direction. But on the other hand, a climber could choose the steepest path, which would actually be, if you think about it, just intuitively, you could guess that it should be something which is perpendicular to the level curve. And in fact, this is something that we have confirmed by calculation, and I will go over it one more time in a couple of minutes. So in that case, the rate of change is the highest possible. So in this direction, the rate of change is 0. In this direction, the rate of change is maximal. And if we go in a direction which is perpendicular to the level curve, but we go down, then it's going to be minimal, the smallest possible. Well, its absolute value is still going to be the highest possible, but it's going to have a negative sign. So as a number, it will be the smallest possible value. So here, rate is minimal. Okay, and so so in order to talk about the rate of change, you have to choose a direction. That's why it's a directional derivative. There isn't a single derivative for a function in two variables, but there is a whole variety of derivatives. A derivative is determined by the choice of the direction. Okay, so what are the variables here? Which variables am I talking about? Well, the variables are somewhere here. So there is let's actually do it. Let's do it on this board, because I don't want to mess up the picture. So I want to draw the coordinate system. And let's say this plateau, this plane, xy plane, is the sea level. And the z then will correspond to the height, to the altitude above the sea level. Now our point has a projection onto the plane, and so on the plane it has coordinates x and y, or maybe x0, y0, to emphasize that these are some fixed numbers. So these are the coordinates this corresponds to the position of the climber. You see, the point is the climber is in space, right? So a priori the climber has 3 coordinates, x, y, and z. But because the climber is not flying, he's not jumping with a parachute, he is on the mountain. Because he's on the mountain, as soon as we know the x, y coordinates, we know the z coordinate, unless the mountain has a shape which sort of comes back, right? But normally, normal mountain, for a normal mountain, it's not going to happen, right? So then the z coordinate is actually determined by the x, y coordinates. That's why the only parameters here are x and y, and not x, y, and z. In fact, you can think of this surface as a graph of a function. Graph represents the mountain. Okay, and so now when we talk about the direction, we can think about the direction as being the direction on the mountain, but we can also think about the direction as being the direction on the xy plane. And so, in other words, what we can do is we can drop the level curve down here, and it's not going to look exactly the same because I have kind of magnified the picture compared to the picture there. This is bigger. I have used a different scale for the bottom picture as opposed to the top picture. So the level curve will look like an ellipse, but I have magnified it. I have rescaled it to make it bigger so that it's easier to draw. So then the directions which we have talked about here are the following. This one goes parallel to the level curve. that's the direction along the xy plane or in the xy plane, which would correspond to the movement on the mountain parallel to the level curve. This is the direction on the xy plane, which will correspond to to the path of steepest ascent, for which the rate is maximal. And this will be the direction for which the rate will be minimal. So this is what we call the rate of steepest descent. Now, I would like to draw these vectors actually to be in such a way that they are of the same length, because they are supposed to be unit vectors. This is a convention. We agree from the beginning that we will measure directions by unit vectors. Okay. And the point is that these are perpendicular. So what are these vectors? This again is a vector parallel to the level curve, and this vector is a vector perpendicular to the level curve, and this is what we discussed last time. I mean, both of these vectors are perpendicular to the level curve, and the one which corresponds to the steepest ascent is the one which is the gradient vector. So this is actually the gradient vector. So this is Nablaev. Because to get the steepest ascent, you have to go inside this level curve, right? Because you go towards the center of the mountain, and this one will be negative. It's negative. And the point is that I explained last time why this gradient vector is actually perpendicular to the tangent vector, or in other words, perpendicular to the tangent line, to the level curve. This is some calculation which involved the knowledge of equations for lines on the plane. Okay? So that's the picture. But in principle, there are many other directions we can also draw. We can also draw a direction like this, say. Again, some unit vector, u, which would be AB, which will have two coordinates, A and B. And if the climber goes in this direction, then her path would go along that, and it will correspond to some path on the mountain, like this, which is neither the steepest ascent nor the steepest descent, nor is it parallel to the slope. You see, in this case, it goes down because the vector points outward. So this direction, or more precisely, this line, which contains this vector, will correspond on the mountain to some specific path, which starts at this point and then goes somewhere. Okay? And what we are calculating is just the slope of that curve, of that path. So the directional derivative d sub u f x0 y0 with respect to this vector u is the slope of the path on the mountain, or on the graph, corresponding to the line containing u. You see, this is the line I'm talking about, this yellow line. Well, I didn't draw it very well. Maybe it's more like, it more goes like this. So if I look at this line will give me that path. What do I mean by give me? If I lift that path, there's a path on the on the xy plane, but it has a unique lift to the graph. This is the yellow path on the graph. In other words, this line, or this half line, is the projection of that path. There's a unique path on the mountain which starts at that point, and whose projection onto the xy plane is the half line directed by u. You see what I mean? Are there any questions about this? Okay. So the point is that the graph is two-dimensional. It's a surface. But once you choose a direction, you cut a path or a curve on that surface. So you are back to the one-dimensional case. And in the one-dimensional case, you can actually talk about the slope. Because you get a graph of a function in one variable, namely the variable along this line, and you can talk about its slope. That slope is the rate of change along that path. That's what we call the directional derivative. And finally, we have a formula for it, which involves the gradient vector. Which involves the gradient vector. And this formula tells us when this directional derivative takes some particular values. For example, the maximum value corresponds to u equal nabla. Minimum value is its opposite. And the zero value corresponds to the tangent, to the u, which is tangent to level curve. Okay? But this we already knew by analyzing this picture just on the grounds of common sense. We didn't need to do any calculation to figure this out. In fact, when you are climbing the mountain, you are not pulling out a paper pad and a pen and starting to calculate what is the best way to reach the top of the mountain. You kind of follow your intuition. And what your intuition will always tell you is that if you want to reach the top in the fastest possible way, you have to go perpendicular to the level curve, in direction perpendicular to the level curve. And likewise, if you want to go down the fastest way, you also go perpendicular to the level curve. Is that clear? Okay, so intuitively it's clear, but now we have proved it because we found a formula for the rate of change, and from this formula, written in terms of dot product, it's plain obvious when it takes the maximal value, the minimum value, or the zero value. And that was one of the main conclusions last time, but now I have illustrated it in this way. Okay. So now, one more. Oh. That's odd. Here is a problem. That's called catch-22. All right. So I have this is a small inconvenience. But that's very clever. I will not try to get it out of there because I don't want to put the second one. So yes. What is that? What is that symbol? It's called nabla. It's a Greek letter, which is written opposite to delta. But we're using it for the gradient. I'm sorry? That's right. This is a notation for the gradient. Okay. So, and one other thing which I wanted to mention in this regard is we talked about equations of we have talked about equations of tangent lines and tangent planes. And I know that this could be confusing because you have many different objects at the same time for which you can look at tangent lines and tangent planes. Seems like there are many different discussions going on. the same time. Okay, let's focus. Okay, so the tangent lines and tangent planes. And so I just wanted to summarize the stuff once more so that there's no ambiguity, there's no confusion. So the first is a two-variable case. Two-variable case. In the two-variable case, we look at the level curve of a function f of xy. So it is given by this equation, xy equals k. So that's this level curve. That's this curve of equal height or equal altitude, which I drew over there. Okay, and so then we can look at the tangent line to this curve. And the equation of this tangent line at the point x0, y0 is like this. It's f sub x at x0, y0 times x minus x0 plus f sub y 0, y0 times y minus y0 equals 0. Okay? But in fact, we can now look at the case of three variables as well, right? So let me do it here. Three-variable case. In three-variable case, we would want to take, instead of a function in two variables, f of xy, we would want to take a function, maybe f capital, a function on three variables, x, y, z. And by analogy, we would have to look at the level, but not curve, now level surface. Level surface of this function. And so that would be f of x, y, z equals k. Maybe I should say that k is some number. K is a number. So that's, for example, in this discussion, k would be the height. So I don't know, 1,000 feet. Whereas x and y and z are variables. So that's the difference. It's an equation. It's one equation for three variables. Because in this equation, this is some number, like 1,000. So then you can ask, what is the equation of the tangent, but now not line, but plane, to this surface at the point x0, y0, and z0. And you see, the point is that the answer is given by something which looks exactly the same, except now we have three variables. So we have to add one more term, which involves the third variable, z. So what the answer is the following. You have to take the partial derivative with respect to x, multiply by x minus x0, plus the partial derivative with respect to y, plus the partial derivative with respect to z now, also. You see. So the difference between the two-variable case and the three-variable case is that we now have an extra variable. So everything gets dimension one higher. Dimensions get bumped by one. We had a curve, now we have a surface. We had a line, now we have a plane. The equation here involved two partial derivatives and had this very simple form. And now the equation involves all three partial derivatives, but has the same form. Okay? So I will not derive this formula. It is derived in the same way as in this case, in the case of two variables. But it's sort of, I hope it looks convincing to you because you can clearly see the analogy. And in fact, if you want to prove it, you can prove it in exactly the same way. Now, what is slightly confusing in this is that there is a special case of this three-variable picture. And the special case is when f of x, y, z is f of xy minus z. So you can ask, why would we even bother to look at this special case? And the reason is very simple, because in this special case, if I look at the equation f of x, y, z equals 0, which is a special case of a level surface, namely the case when k is 0, right? This is just the equation z equals f of xy. And this equation defines a graph of the function in two variables. So it's kind of funny that function in two variables shows up in two different contexts. It shows up here in the context of level curves, okay? But it also can show up here for functions in three variables, even though it is a function of two variables. But even when we have a function in two variables and we think about graphs, we automatically go to the three-dimensional situation, right? And so the graph of a function in two variables can be thought of as a level surface for a function in three variables. Which function? Well, this function, f of xy minus z. It's kind of a simplest concoction you can make out of f and the new variable z. So we can apply this general formula for the tangent plane to this special case. And what do we get? Let's observe that f sub x is just f small sub x, because when you take partial derivative of this function big F, you have to differentiate this one, that would be just f sub x, and you differentiate this one, but this one is independent of x. So this doesn't change anything. So the partial derivative of the function of this function of this whole function with respect to x is just a partial derivative of this part. So it is small f sub x. Partial derivative with respect to y is f sub y. Partial derivative with respect to z is what? Negative 1. It's negative 1 because that's the derivative of this function, negative z, with respect to z. This guy doesn't depend on z, so its partial derivative with respect to z is 0. But the partial derivative of this term is negative 1. So we get this three partial derivatives, which we substitute into this formula. And what do we get? We get f sub x of x0, y0 times x minus x0 plus f sub x0, y0, y minus y0 minus z minus z0, okay, equals 0. And now we recognize the equation of the tangent plane to the graph, which we have known already. This is the one which we got already 2 weeks ago when we talked about differentials and linear approximation. The only difference is that now I put negative z minus z0 on the left-hand side, but in our old discussion, we would write equals z minus z0. And then we would switch the left and right-hand sides too, but that's a minor issue, right? So this is just a slightly different form of writing the same equation, just putting everything on one side. And now you see that the case of graphs of, the case of tangent planes of graphs of functions into variable can be thought of in two different ways. Okay? Namely, you can think that you started with a function in two variables and you just look at the graph and you look at the tangent plane. But you can also think of it as a special case of the more general case of functions in three variables, except you take as a function in three variables this very special form, f of xy minus z. In either way you approach it, you get the same answer. But now you can appreciate more the connection between this answer and this. Many people ask me after last lecture why when we look at the equation of the tangent line of function in two variables, it's as though we are dropping this term, z minus z0. So there is this negative 1 in the, which we just drop. Well, geometrically it's clear. In fact, the board stayed since Tuesday. So I guess nobody likes this small board except for me, which is good. So this is this tangent line, and this tangent line corresponds along this tangent line to the level curve. We have the same value of z equals z0. So that's why we drop this term to go from this equation to this. So you can get this equation from this by dropping z minus z0, because z is equal to z0 along the level curve. But also you can now understand that this formula is a special case of the formula for the tangent plane to a general level surface, which actually looks like this one. Except we have a third variable. In the special case, when the function is like this third term becomes extremely simple. It just gets a coefficient -1, so you just get minus z minus z0. Okay? And to make the analogy complete, let's actually look at the, let's fill in this square. You know, it's like when you do IQ tests. I've never done it, by the way. But I know it's easy to find them online. And I think the problem is often like fill in the square. So this is exactly the kind of question here. What should be here, right? In other words, this is a case of 3 variables, and this is a special case of that, right? Now, what's the analogous special case for functions in 2 variables? That's the case when this function of 2 variables, special case, when this f of xy is some function in 1 variable, let's call it g of x minus y. And so you see, in this case, in fact, you know what I'm going to do to make it look more like an analogy. Let's reposition the boards. There we go. So now I think it's more clear what I mean by filling in a square. I want to find a special case of this, which is analogous to how we found the special case of 3 variables. And that's the case when now our function in 2 variables is equal to another function in 1 variable minus y. Okay? In this case, the equation f of xy equals 0 means y equals g of x, right? And this is a graph of the function g of x. So a level curve for a function of 2 variables can become the graph of a function in 1 variable when this function in 2 variables has this special form. Did you have a question? Good question. So what would happen if we put some k, right? If we put some k, then it would be here minus k. I would put minus k, right? So then I could just absorb k into the definition of the function g of x. If I redefine my function g of x by subtracting k, then I would get back the level 0. So that's why we don't lose any generality by looking at the case of level 0 rather than as opposed to general case. So let's just look at the case of level 0. Okay, so that's a graph. And so now this formula for the tangent line, note that f sub x of xy now is g prime of x. Just like here, the partial derivatives of the big function f for respect to x and y were just the derivatives of the small f. And now the role of the small f is played by g. So the partial derivative like this is just g prime. And the partial derivative with respect to the second variable is -1 again. Because this minus y now plays the same role as minus z played here. So when we take the derivative, we get -1. So now this formula for the tangent line becomes g prime of x 0 times x minus x0 minus y0 equals 0. Let me rewrite this. This is equivalent to saying y is equal to f prime of x0 times x minus x0 plus y0. We recover the old formula for the equation of the tangent line to the graph of a function in 1 variable. That formula is exactly this one, right? The slope is f prime. You multiply x minus x0, and you add the value of the function at at the point x0, which is y0, right? So there is nothing mysterious in these formulas. In this special case, we get back the old formula we've known all along. And also, this now sheds some new light on this coefficient -1, which many of you have found mysterious. It's not mysterious. It's as mysterious as this coefficient -1, which shows up in the old formula for the tangent line to the graph. We were not surprised to write the formula for the graph of the function is y equals f prime times, in this form. But if you have it in this form, you can rewrite it like this. And when you rewrite it like this, you find the coefficient -1. That's exactly the reason it appears is the same reason why this -1 appears. Okay? Any questions about this? Yes.
It's not apparent to me why we choose this special case.
Why do we choose the special case? That's a very good question. Why do we even choose the special case? Well, from the point of view, let's talk about this case. From the point of view of functions in two variables, this sounds strange. Why would you write it like this and not f of x minus xy or something, right? So from point of view of functions of two variables, it doesn't make any sense. It makes a lot of sense, however, from the point of view of the theory of functions in one variable. When we study functions in one variable, we would like to visualize them by graphs. Right? When we draw a graph of function one variable, we introduce one more variable, and we look at the graph, which is y equals f of x. What I'm saying now is that within this formalism that we are developing, we can think of the graph of g of x, which normally we would write as y equals g of x, just in this form. And when we write it in this form, we never say the word level curve or anything like this. We just say graph. But we have to realize, it's important to realize, to see the connection between different formulas, it's important to realize that this graph actually can be thought of as a level curve for a function in two variables. And that function just happens to be this function, even though it looks kind of, there's no reason a priori to study such functions. We have introduced them because we started from the point of view of functions in one variable, and then this will naturally fell out once we started to look at the graphs. So that's likewise in this case. Okay, yes?
So would the analog of a level curve in a function of one variable just be a point?
That's right. It could be a point or finitely many points. Because you could be, let's look at the function. And for a good reason, right? If the dimension of the level curve is going to be the number of variables, or level curve or level surface and so on, would be the number of variables involved minus 1. If you have two variables, it's a level curve, so dimension 1. There are three variables, it's a level surface, dimension 2. If it's a function in one variable, it will be of dimension 0. And zero-dimensional objects are just collections of points. And the way it works is just like this. Let's look at, for example, if you have a parabola, the level curve consists of 2 points. But if you have a cubic parabola like this, there will be 3 points. And if you have a cosine, you will actually have infinitely many points. Infinitely many points if the level is between 0 and 1 and -1. And if the level is higher than 1 or lower than -1, then it will be empty. Level curve could be empty, or level surface. In this case, it's sort of level point. But we don't have a good word for a collection of points. So it's like zero-dimensional object, manifold, or as a mathematician would call it. Any other questions about this? Yes?
Why in one box do you have g prime of x0, and then in the other one you have f prime in the two boxes?
Oh yes, I'm sorry. Thank you. That was just that was a mistake. Thank you. Yeah, it's g prime, of course. I mean, I'm just saying that this formula becomes this formula, but I called it g, right? Sorry. Yeah, I completely messed it up. All right, good job. Okay. So that will do it for us in this topic, and actually we are running out of time, so we need to talk about something else today also. I really wanted to go over this slowly to emphasize the connection between these different objects, because I think that there are different dimensions and different number of variables at play, and it could be very confusing. But I think that if you put this in this sort of in this picture where you have these 4 squares, 2 variable case, 3 variable case, special case in 2 variables, special case in 3 variables, then I think it becomes much more clear. All right. But the next topic we'll discuss is concerns finding maxima and minima of functions. And as is always the case, it's actually instructive to look at this question already in the one-dimensional, in the one variable case. Because we already can gain some insights into the problem by looking at this very special, the simplest possible case. If you have a function in one variable, it's a natural question to ask where this function attains maximum and minimal values. That's important because this function could correspond to something in real life, and you may want to maximize that or minimize that. And so the first point I want to emphasize is that there are 2 different types of maxima and minima: the local and the global. Or the global ones are called absolute. But I like to think local, global kind of. I like this terminology a little bit better. So what do I mean by local? So let me draw this. For a function one variable, it is very convenient to analyze everything by using graphs of functions. And graphs, again, are curves on the plane, right? So we introduce the new variable y, and we write a graph as given by the equation y equals f of x. So let's look at this. Let's look at this kind of function. That's a very typical example. So I want to focus on this point. So clearly, this point, the value of the function at this point, so this would be the point x0, and that's the value of the function. This is f of x0. The value of this function at this point is greater than the value at nearby points. So that's an example of a local maximum. A point is a local maximum if there is a small neighborhood of this point such that if you restrict your function to this neighborhood, which is this little interval in this case, then this function will be the maximum value on the interval. Okay? But is it a global maximum? Clearly not, because I have a point here, for example, x1, for which the value is higher. So that's not a global maximum. That's not a global maximum either. In fact, in this example, there is no global maximum because I'm assuming that the function keeps growing, keeps increasing as x is increasing. Okay? If that's the case, there is no global maximum. So global maximum is a completely different, finding global maximum is a completely different game than finding a local maximum. Finding local maximum just involves analyzing the function on a very small interval around this point. Finding global one sort of involves analyzing all points in your domain. The way I phrased the question so far, I have phrased the question so far is as though we were studying global maximum on the entire line, on the entire x line. Okay? And you see clearly that question often doesn't have an answer. In other words, there is no global maximum. Simply because for any point, there will be another point which will have a higher value, and so on. Okay? So the question of finding global maxima, it is better to phrase on domains which are bounded. Not on the entire line, but on bounded domains. Bounded means that it's finite. So it's better to say what is the maximum of this function on this interval. Okay? This is an example of a closed bounded domain in the following sense. First of all, it's bounded because it's finite. It doesn't go to infinity. Second, it is closed because it contains the endpoints. And these are the kind of domains that we should look at if we want to ask questions about global maxima or absolute maxima and minima. So let's look at this question in this particular case. In this particular case, we see that the maximum value is actually taken at this point. This is a maximum. So now you can appreciate why you have to include the endpoint. If we did not include the endpoint, there wouldn't be a maximum, because no matter how close you are to this point, there will be another point even closer for which the value would be even higher. So therefore, there will be no maximum, right? So in order to guarantee that you have a positive answer to the question of existence of maximum, or minimum for that matter, you should really look at closed and bounded intervals. And then what happens is that the maximum can be attained either at the boundary, which is the case here, or it could be some local maximum which lies in the interior of this interval. In this particular case, you do have a candidate. You do have a candidate for a maximum, this one, because it is a local maximum and it is within this interval. But it's not a global maximum on this interval because the value of this function is just bigger. But if I were to take a different interval, if I were to take an interval like this, for example, okay, then this guy would win, because at the boundary, the value would be smaller. You see, at the boundary, the value would be smaller. So this guy would have the highest possible value on this interval. So the bottom line, the upshot of all this, is that the absolute maximum can be found in a finite set of points. And those points are, first of all, the endpoints, and all the points where you have potentially local maximum minimum. So the global maximum on the interval, on a bounded interval, on a closed interval, bounded interval, let's call it AB, can be found maximum of some function f at one of the following points. One of the following points. The endpoints, which are AB, and the points of potential local maximum. And here it's important to emphasize the word potential. And those are the points for which f prime of x is 0. Because certainly, if it's a point of local maximum, then the slope of the tangent line at this point is going to be 0, right? Because if you have a non-zero slope, just move away from this point, and you'll get a bigger or smaller value. On one side bigger and on the other side smaller. So the only way you can have possibly have a local maximum is to have slope 0, and slope is a derivative. So that's why these are the points for which the derivative is equal to 0. Okay, so this is the first statement that I want you to remember, or recall perhaps from the one-variable calculus, which is that if you're looking for global maximum, what you need to do is simply measure or evaluate the function at the endpoints. Evaluate at this point, evaluate at this point. Next, find all the points where the derivative is 0 and evaluate the function. So you get a finite list. And then just pick the one or the ones where the value is maximal. These are the values, these are the maxima of this function on this interval. In other words, you don't have to look through all the points on the interval. There are infinitely many. But you only look at the endpoints and the points where f prime is equal to 0. That's the algorithm for finding maxima of a function. And likewise for minima. Just replace the word minimum by maximum by minimum. So it's exactly the same. Now, so before I go and generalize it to the case of two variables, I want to explain what I mean by the word potentially, potential local maximum. In other words, if the point x is a local maximum, or minimum, then the derivative is 0. I already explained this because the slope has to be 0. If it's a maximum minimum, slope has to be 0. If the slope is non-zero, it means you can increase or decrease the value by moving a little bit away from the point. So this is true, but this is not true. This is not true. In other words, if the derivative of your function at your point is 0, it doesn't mean it's an absolute maximum or minimum. And the reason is the following. The reason for that is the following. There's a very simple counterexample to this, namely the function x cubed. So f of x is x cubed. F prime is 3x squared. And so f prime of 0 is 0. Which we see, right? We do see that the slope at 0 is 0. Right? But is it a point of a local maximum or minimum? It's not, because if you go this way, it increases, and if you go that way, it decreases, right? And in fact, if you think in terms of monomials, the same thing will happen if you have x to the odd, to the n where n is odd, like 3, 5, 7, and so on, because the derivative of x to the n is n times x n minus 1, so it's always 0 for this function. But if n is odd, then for positive x, this value is positive, and for negative x, it's negative. So it's going to look like this. But if x is, if you have yx to the n where n is even, so it's 2, 4, and so on, then it's going to look like this instead. And so in that case, it is okay. It is actually a point of a local maximum minimum. A local maximum in this case, and if it were negative, it would be local. Sorry, this is minimum, but if it were like this, it would be maximum. So in other words, there are many possible scenarios where you have a derivative equals 0, and it is a maximum. And there are many scenarios where the derivative is 0, but it's not a maximum or minimum. Okay? So it only goes this way. If it is maximum minimum, then the derivative is 0. That's why I said those are the points which potentially could be maximum or minimum. Okay? So in principle, you could rule some of them out from the outset by saying, well, these points are actually f prime is 0, but the point is not maximum minimum. So then it cannot possibly contribute to the list of suspicious points or candidates for global maximum minimum. But I think it's just much easier to just take all of them, because they're going to be finitely many, and just evaluate your function f at all of them, and then compare. Where do you get the largest value, and where do you get the smallest value? You guys following this? Okay, good. So, so that's why the way I formulated this, I didn't want to, at this level, to try to differentiate between the ones which are actually maxima and minima and which are not. I just said, let's look at all which are potentially maxima and minima. Okay, so that's the one-dimensional case. And now, in some sense, we already know everything we need to know, because in the two-dimensional case, it's going to look exactly the same. The criterion will be slightly more complicated. Maybe I'll say one more thing, which is that there is a criterion to see whether the function is a maximum minimum in this case. Namely, suppose that f prime is 0, but f double prime at x, f double prime at this point. Let me emphasize that it's a particular point x0, which was the point 0 in my previous example. But let's call it x0. This is positive. Then it's a maximum. It's a minimum, sorry, minimum, local minimum. And if, I didn't say but, it should be and. If f prime of x0 is 0 and f double prime of x0 is less than 0, then it's a local minimum. In other words, if you think about this in terms of Taylor series, you can approximate, oftentimes, you can approximate a function by a smooth function by its Taylor series. And the first terms on the Taylor series are going to be given by the value of the function, then the derivative, and then the second derivative. So the point is that if the first derivative vanishes, that's the necessary condition to have a local maximum minimum. But then it depends on which term in the Taylor series is non-zero next. So for example, if the second term is non-zero, that means your function looks like x minus x0 squared times some coefficient, right? What I'm trying to explain is the following. Let me do it more slowly. The Taylor series looks like this. Okay? So this is just the value of the function. Let's assume, without loss of generality, that it is equal to 0. I mean, after all, we can just subtract this value from this side. It's not going to change anything. So let's just assume that it is 0. So the next comes this term, which is the first derivative. And the first derivative has to vanish. Otherwise, it can't be a maximum or minimum, as we just discussed. So this also vanishes. So the next term is the second derivative, times x minus x0 squared. And then there were some additional terms. But the additional terms are negligible compared to this term when x is very close to x0. So you might as well replace your function by this function. But this function is just a parabola. I mean, the graph of this function is just a parabola. And the parabola, we know, the parabola would be like this if the coefficient is positive. And it would be like this if the coefficient is negative, right? So in this case, clearly this is a local minimum for this one. And for this one, it's a local maximum. And the other terms don't matter. So that's the reason why we get this criterion. But if it is 0, if this term is also 0, then we can't really tell, because we don't know what comes next. If the next non-zero term is, say, cubic term, we know it's not going to be maximum minimum because we looked at the cubic parabola, and it's like this. It doesn't have a maximum minimum, right? But if the cubic one vanishes, but the quartic one is non-zero, then again it's good. It's a good shape. It's a U shape, right? So there is no telling. We should really then look at higher terms in the expansion, and that's much more difficult. So that's why we just stop here and we say, well, here's the criterion. If the first derivative is 0, but second derivative is positive, it's a local minimum. And in this case, it's a local maximum. And we just stop right there. In other words, it does not exhaust all possible cases, but it concerns or helps us in the cases when the second derivative is non-zero. And there is a similar criterion also for functions in two variables. So now we switch to functions in two variables. I wrote what? On the top of what? Oh, they're both local minima. Wow. It's kind of pessimistic. Thank you. I have to correct. We definitely should correct that. Otherwise, it looks like we never reach maximum. Okay. I think now it's good. Right, because if it's negative, it's shaped like this. So it is maximum. Okay. Okay. So now switch to functions in two variables. So again, we have local things, local maxima and minima, and global ones. And searching for them is sort of the two different games for this. For local maxima and minima, the first step, step one, is to check that the two partial derivatives are 0. Just like for functions in one variable, the first step is to look at the first derivative. Well, now we have function in two variables, so there are two different partial derivatives. So both of them have to vanish in order for us to have a local maximum minimum. Well, I'm assuming now that both of them exist. There is another possibility, which is that, say, one of them may not exist. And in that case, that's also a possible case for local maximum minimum. But let's assume in this discussion that the partial derivatives always exist, so then we don't have to worry about this. If they do exist, then a given point, x0, y0, will be a local maximum or minimum only if the two partial derivatives, both partial derivatives vanish. So when you kind of narrow down your search, you first have to, you throw everything away, everything else away. You just keep the points for which both partial derivatives are 0. But this does not guarantee that it is maximum or minimum. Just like in the one variable case. The best we can do is to have a criterion involving second partial derivatives. And so the criterion, we would like to say something like, if the second derivative is positive, it's a minimum. If it's negative, it's a maximum. But there are now three different second partial derivatives. We have f sub xx, f sub xy, and f sub yy. Okay? So in fact, the rule is as follows. We have to calculate the following expression. So remember when we did cross products, we used determinants. So let's make a determinant of this 2 by 2 matrix, which is very easy to memorize. Think of the x as think of this one corresponding to the first index, and this, the rows will correspond to the first index. So first index here is x and here is y. And the colons will correspond to the second index, which will be, here is x and here is y. So you put 4 possible partial derivatives in this matrix. Then, of course, we know by Clairaut's theorem that this is the same as this. But let's not yet worry about this. This is just an easy way to remember. OK. And then we take the determinant of this. So what's the determinant if fxx, fyy minus fxy, fyx? But fyx is equal to f. OK, now we remember it. Now we remember it, and we just put square. So let's call this D. So the criterion is that if both partial derivatives are 0 and D is greater than 0, then it's a maximum. That's number 1. Number 2, if both partial derivatives are 0 and D is negative, then it's a minimum. And finally, I'm sorry, I'm not saying it correctly. It's maximum. No. Sorry. It's worse. It's worse than that. It's maximum or minimum. Then this one is not. Let's just say not. I don't have enough space, but not a maximum, not a minimum. If it's negative, and if it is 0, it's inconclusive. Don't know. Okay? So, first point, think of this as an analog of this rule. Because in the case of one variable, there is also a rule which involves the second derivative. However, this rule is much more complicated because there are 3 different partial derivatives of second order, and we make some complicated combination of them. Whereas here we just took the second partial derivative on the nose, and we just looked whether it's positive or negative. But there is an analogy between the two clearly, because this involves second partial derivative, and this involves second partial derivatives. Okay. Now, but it looks very mysterious. Why do I make this? Why do I look at this combination and not at other combinations? To understand this, think of the case of parabola, of the analog of the parabola. Because I explained to you how this rule came about by looking at the parabolas, right? The parabolas, because the parabolas approximate your graph, right? Just because of the Taylor expansion argument, you can see that parabolas are going to approximate your graph near the point of where the first partial derivatives or first derivative vanish, right? So think about the parabolas. And in the case of the parabola, you know that if it's an elliptic, well, first of all, parabola now becomes paraboloid. But there are 2 types of paraboloids. There is an elliptic paraboloid and there's a hyperbolic paraboloid. Okay? And just look at the examples of elliptic paraboloids, and you will see that for elliptic paraboloid, the first condition will be satisfied. And for hyperbolic paraboloid, the second condition will be satisfied. So if z is equal to, so let's say f of xy is x squared plus y squared. Let me just write ax squared plus by squared. Okay? So what are the derivatives in this case? fxx is 2a, right? fyy is 2b, right? And fxy is 0. So there is a simplification in this case that there is no cross term. Okay? So this matrix looks like this. It's 2a, 2b, and that's 4ab. That's the D in this case. So to say that D is positive means to say that both AB are positive or both of them are negative. Right? If both AB are positive, it's going to look like this, right? if both A and B are negative, it's going to look like this. Right? So in this case, it's a local minimum. In this case, a local maximum. But in both cases, you see, AB both positive, AB both negative, the combination A times B, or 4A times B, is in both cases is positive. So that's why we get into the first condition, in the situation of the first condition where D is positive. So in this case, we can say for sure it's maximum or minimum, but we cannot say which one. So we have to look at it more closely. Okay, and what if D is negative? If D is negative, that means that A, B have different signs. And in this case, so a good example of this would be x squared minus y squared. And that's a hyperbolic paraboloid. And for hyperbolic paraboloid, I drew this picture before. It looks like a saddle. And on a saddle, there is a point from which you can either increase the function if you go along one of the parabolas, which goes up, which opens up this way, or you can also decrease the function by traveling on a different parabola, perpendicular one, where it opens up downward, right? So this point clearly, this point on the saddle is not a point of maximum or minimum. So that is the explanation of this criterion in the case of quadratic functions, functions which are combinations of x squared and y squared. And the point is that all other functions can be reduced to these ones by a certain procedure. And that's how you get this rule. Okay? So that's how we get this rule for local maximum and minimum. And that takes care of that issue. And the last remaining topic then is how to find the absolute maximum and minimum on particular domains. And this I will illustrate very quickly by a concrete example. This was step 1, and this is step 2. Okay. Let me give you an example of how to find maxima and minima, global maxima and minima. I have just enough time to explain this. Okay. So let's say you have a function f of xy, which is x squared plus y squared plus x squared y plus 4. Find find maxima and global or absolute maxima and minima on the domain x, y, where absolute value of x is less than or equal to 1, absolute value of 1 less than or equal to 1. Okay? So the first step is to sketch the domain. Sketch. It's very easy, right? So this is just a square where the sides are lines parallel to xy axis at 1 and negative 1. So step 2 is to find the boundary. Identify the boundary. This is the boundary. And now we are going to make a list of suspicious points, or points which are candidates for being maxima or minima. Okay? And this list will include 3 kinds of points. first are points in the interior where both partial derivatives are 0. What do I mean by interior? Interior means everything except the boundary. Okay? So I have to calculate what is fx and what is fy. Fx is 2x plus 2y. And fy is 2y plus x squared, right? So we have to set this equal to 0 and this equal to 0. Since I'm running out of time, let me just go to the next step. So you solve these equations. It's very easy, right? So this is the first group of points that you get on your list. The second group of points are points on the boundary, but which belong to the smooth part of the boundary. Two is smooth part of the boundary. Yes. 2x plus 2xy. I'm sorry, that's right. Thank you. All right, smooth part of the boundary. What I mean by this, well, we exclude this, I mean, maybe it's not a good idea to say smooth part. Maybe it's not like this. Let's just say, let's just call them components of the boundary. Components of the boundary. So what I mean by components, I mean these 4 intervals. So break your boundary into pieces which can be represented by a nice equation, like here. Here is like x is equal to 1 and y is between -1 and 1. So then restrict your function. Restrict your function to this component. It will effectively become a function in one variable. Solve the problem for this one variable function. Okay? 1 minute left. Okay. So let me give you an example. Say one of the components is y equals 1 and x is between -1 and 1. So I substitute this y equal 1 into this formula and I get f of x1 is x squared plus 1 plus x squared plus 4. So that's 2x squared plus 5. Right? I got a function in one variable on this interval. Find the absolute maximum of this function on that interval. Okay? So, and then the same for each other component. And finally, and that's not all. It would have been all if you didn't have the corners. But because you have corners, you have to include them, because in principle it could happen that the maximum minimum is attained at the corners. So include the corners too. So now you compile the list and you evaluate the function and you choose the one where the value is maximal. So that's how you do it. All right, have a good weekend.